In the name of Almighty God, I am Master Sankosha, and today I want to talk about Introduction to Acoustic Module. The acoustic module consists of a set of physics interfaces that enable you to simulate the propagation of sound in fluids and solid in a fully multiphysics-enabled environment. The available physics interfaces include pressure acoustic, elastic waves, acoustic solid interaction, acoustics, detailed convected acoustic models, and fluid-induced noise. Thermoviscous acoustics, ultrasound, geometrical acoustics, and pipe acoustics. For acoustics analysis covering the frequency range from infrasound to ultrasonics as well as many formulations of the underlying equations, the acoustics module incorporates four numerical methods including finite elements methods, boundary elements methods or BEAM, discontinuous Galerkin or DGFM, and ray tracing. As you see, the first figure shows capsule model of the sound pressure level distribution in a muffler system. Acoustic simulations using this module can easily solve classical problems such as scattering, diffraction, emission, radiation, and transmission of sound. These problems are relevant to muffler design, loudspeaker construction, sound insulation for absorbers and diffusers. The evaluation of directional acoustic patterns like directivity, noise radiation problems, and much more. The acoustic structure multiphysics couplings enable modeling vibroacoustic problems involving structure and fluid-borne sound and their interaction. For example, acoustic structure interaction is simulated for detailed muffler design, ultrasound, piezoacoustics, sonar technology, and noise and vibration analysis of machinery in the automotive industry. Using the capabilities of capsule multiphysics, it is also possible to analyze and design electroacoustic transducers such as loudspeakers, sensors, microphones, and hearing aid receivers. The propagation of elastic waves can be modeled in solids and porous materials as well as in coupled problems. Air acoustic problems can be analyzed and modeled by solving the linearized potential flow equations, the linearized Euler equations, or the linearized Navier-Stokes equations. These equations are used to model the one-way interaction between an external flow and an acoustic field, so-called convected acoustics. Applications range from jet engine noise analysis to simulating acoustic flow sensors, linear systems with a bias and/or grazing flow, and mufflers with flow. Fluid-induced noise can be modeled using the light-hill acoustic analogy or the array acoustics wave equation. This analysis requires a detailed less or dense flow analysis available with the CFD module. Flow data available in the CGNS format can be imported and mapped. The thermoviscous acoustic interfaces can accurately model systems having small geometrical dimensions where thermal and viscous boundary layer losses are important. This is relevant to the mobile phone and hearing aid industries, for all transducers designers, and for modeling the true properties of the metamaterials. For MEMS transducers, a slip wall formulation can be added. In the time domain, nonlinear effects can also be included. The first figure shows capsule model of an ultrasound flow meter modeled using the convected wave equation interface. The model includes interaction with a steady-state background flow. The ultrasound branch includes two interfaces: the convected wave equation Time explicit interface can be used to compute the transient propagation of linear ultrasound acoustic waves over large distances. Relative to the wavelength, the nonlinear pressure acoustics time explicit interface can be used to model the propagation of high amplitude nonlinear acoustic waves. Both interfaces can be coupled to the elastic waves, a time-explicit interface, and the piezoelectric waves, time-explicit multiphysics interface, and the interfaces under the ultrasound branch are not restricted to high-frequency propagation but can in general be applied to any acoustically large problem. Geometrical acoustics includes the ray acoustics and the acoustic diffusion equation interfaces. These physics interfaces are valid in the high frequency limit where the acoustic wavelength is much smaller than the characteristic geometric features. Both interfaces are suited for modeling acoustics in room and concrete halls. The ray acoustics interface can also be used, for example, in outdoor scenarios. Dedicated functionality also exists for modeling the steady fluid flow, called acoustic streaming, induced by an acoustic field. Acoustic streaming is a nonlinear phenomenon that occurs due to the nonlinearity of the Navier-Stokes equations. Applications are in the biomedical industry such as lab-on-a-chip for cell sorting and more. The acoustic module is of great benefit to engineers by using three-dimensional simulations. Existing products can be optimized and new products more quickly designed with virtual prototypes. Simulation also help designers, researchers, and the engineer to gain insight into problems that are difficult to handle experimentally. Also, by optimizing a design virtually before real life testing and manufacturing it, companies save time and money. Some of the physics interfaces available with this module are shown in the figure 3 and are located under the acoustic branch in the model result when selecting physics. The next section, the acoustic module physics interfaces, provides an overview of the physics interface functionality under each branch. There are many application areas where these physics interfaces are used, from modeling simple pressure waves in air to examining complex interactions between elastic waves and pressure waves in porous materials. For a brief introduction to the basic concepts and theory of acoustics, see the basics of acoustics. The acoustics module application library has many examples of applications modeling, for example, sound insulation lining, loudspeakers, microphones, and mufflers. These examples show, among other things, how to simulate acoustic losses. The loss models range from homogenized empirical fluid models for fibrous materials to those that include thermal and viscous losses in detail using the thermoviscous acoustic interface. Predefined coupling can be used to model the interaction between acoustic structural and electric fields in the piezoelectric materials. See the application libraries window for information about accessing these files. You can also get started with your own conceptual modeling by going to the tutorial example absorptive muffler. And you see in the third figure that the acoustic module physics interface and branches in the select physics wizard. Some physics interfaces require additional modules. The acoustics module physics interfaces. There are nine main branches: pressure acoustics, elastic waves, acoustic structure, interaction, aeroacoustics, thermoviscous acoustics, ultrasound, geometrical acoustics, pipe acoustics, and acoustic streaming. and each of the physics interfaces is briefly described here, followed by the physics interface guide by space dimension and study type, listing the physics interface availability by space dimension and preset study types. The chapter on pressure acoustics. The pressure acoustics branch has interfaces where the sound field is described by the pressure P. The physics interface solves acoustic problems in the frequency domain using the pressure acoustic frequency domain interface where the Helmholtz equation is solved. Transient systems are modeled using the pressure acoustics transient interface where the classical wave equation is solved. Nonlinear effects can be included here using the nonlinear acoustics Westervelt feature. The boundary model acoustics interface is used to study propagating modes in a waveguides and ducts. At a given frequency, only a finite set of wave shapes can propagate over a long distance. You see in the fourth figure, scatter SPL at the odd submarine hull modeled with the asymptotic scattering formulation. To efficiently solve large radiation and scattering problems, the pressure acoustics a boundary element interface solves the Helmholtz equation using the boundary element method. The interface is fully multiphysics enabled and coupled seamlessly with the finite element-based interfaces, both acoustic and structural. The pressure acoustics time-explicit interface uses a time-explicit method based on the discontinuous Galerkin infinite elements to efficiently solve large transient problems. This physics interface can also be solved on a GPU. It can also be coupled to the elastic waves time-explicit interface. Pulse domains can be modeled in the time domain with this interface. Finally, two interfaces exist to model high-frequency acoustics: the pressure acoustics asymptotic scattering interface for scattering problems and the pressure acoustics Kirchhoff-Helmholtz interface for radiation problems. And you see in the fifth figure a three-dimensional bubble plot of the loudspeaker radiation pattern at 3000 Hz from the vented loudspeaker enclosure model found in the application library. The model uses a hybrid FEM-BEM modeling setup. A large variety of boundary conditions are available, including sound hard walls, and the conditions for applying sources. There are radiation symmetry periodic and port conditions for modeling open boundaries. Impedance conditions include models for different parts of the human ear, human skin, simple RCL circuit models, and more. Frequency dependent impedance conditions in the time domain can be set up using the built-in rational fitting approach, and the physics interface also have several fluid models which in a homogeneized way mimic the behavior of sound propagation in more complex media. This includes the propagation in porous or fibrous materials, the paracoustic and anisotropic paracoustic domain feature, the propagation in narrow structures of constant cross-section, the narrow region acoustic domain feature, and fluid models for defining bulk absorption behavior. Monopole, dipole, and quadrupole point sources can also be applied. So-called perfectly matched layers or PMLs are also available to truncate an unbounded computational domain in both time and frequency domain. Finally, the exterior field calculation feature can be used to determine the pressure in any point outside the computational domain. Dedicated results and analysis capabilities exist for visualizing the radiation pattern of the exterior field, near and far field in polar, two-dimensional and three-dimensional plots. Thank you so much for watching my tutorial video until the end. Also, you can download the appropriate files which is related to this acoustic pressure from my github.com/masterscript. Today is 10th of the March 2026, and the time is 8:17 in the morning.